to Juliette.
Thank you, Marina. Hi, everyone. My name is Juliette Uno-Fombon. I'm working for EIT Climate-KIC as well, in a different department than Marina, since I'm working in the Earth Observation and Space department. And so we are partner of a project called EO4Geo, which is co-designing this event today. So the project itself, EO4Geo, is a 4 years project that is financed by the Erasmus Plus scheme, and is grouping more than 20 partners from very different sectors, from academia, local authorities, and private sectors. And all our partners are based all around Europe. So it's a very big project, which goal it is to support the development of skills and knowledge in the Earth observation and geoinformation sector. And so how does the project do that? Well, we are developing a strategy for the whole sector to support skills development. We are creating a set of tools to facilitate recruitment, to facilitate creation of curricula linked to Earth observation and geoinformation, to support this skills development and knowledge creation in Europe. And lastly, the thing that we are doing and that has the most link with today is that the project EO4Geo is developing a training framework with training materials and training actions revolving around Earth observation and geoinformation. And so today, this Spark event is also part of this training framework and is revolving around Earth observation and the applications for climate change. And if at the end of the event you would like to know a bit more about certain topics that we tackle, you are more than welcome to visit the EO4Geo project website and find additional resources there if the topic sparks your interest. Thank you very much and have a good workshop.
Excellent. Thank you, Juliette, and thank you, Marina. I think it's time we move for our first sort of interactive session. So we should all move to the Mirrorboard, and you should have got the link in the email. And we all go to the What I Wonder section, which is, you might be probably want to follow me in the Mirrorboard. I'm there now at the What I Wonder. It's not the, I see that you are all in the left part. You should move to the center where the What I Wonder. Just follow me using Excellent Visiting Explorer. So what is this section about? We would like to know your expectations about the event that we are starting now. So what we are asking you to do is to add sticky notes and one sentence, one word, whatever you want to share. Just tell us what you are expecting out of this event. Sticky notes on the left, you probably are familiar with Mirrorboard if you are, Spark people. And there you go. Be aware not to move all the frames, but I'm sure that you know what you are doing. Right. I still see a lot of people on the left side. You should all move to the center. Right, move to the center. Thank you so much. This is the board. This is the template where we are asking you to place your sticky notes. Okay, I can see people coming there. Good, so good. All right, excellent. You can pick up the sticky notes on the left part. There's a control bar on the left, and then you can drag your sticky notes on the wall and just let us know what your expectations are for the afternoon. can be one word, it can be one sentence, it can be whatever you like. We will reconnect at the end of the event to, that would be a second board where you will be asked to share with us what you actually learned during the event. And we will see, you will see if what you have learned is matching with your expectations. We should all move to the other section, not the introduction, not the introduce yourself, but to what I wonder section, which is on the right side of the board. If you just follow me, you will get to the section. Yeah, I can see some sticky notes coming in. Relaxed and peaceful learning experience. We really hope so. Okay. Okay, we will run this for some few minutes and then we will move on. But in the meantime, please let us know some fancy GIS maps and observation. Yep. Climate change impact, enjoy networking, inspiration. Yes. How to quantify and observe climate change. This is a very, very good point. Understand the scope of Earth observation, how it can be transferred into useful knowledge for tackling climate change. Okay, thank you very much. We will be, staying in this Mirrorboard for during the event, so you might be willing to come back and add a sticky note from time to time. It's not. I would say that we can now move on because we can start our presentations, and I will introduce our first speaker. So it's a pleasure to introduce Edward Escalona, Market Development Innovation Officer of the European Union Agency for the Space Programme. Edward is a space downstream market officer at the EU Agency for the Space Programme since 2019, contributing to downstream market development of Galileo, of the European Geostationary Navigation Overlay Service and Copernicus. Edward obtained his MSc and PhD degrees in telecommunication engineering from the Polytechnical University of Catalonia, and he's co-author of over 70 scientific articles among international conferences and journals in topics related to future internet architectures and services. So welcome, Edward. Thanks a lot for joining us, and I'm leaving you the floor.
Thank you very much, Marco, for the invitation. I'm happy to be here. Let me share my screen and start quickly through the presentation, because it's a pleasure to try to explain what we do at USPA and what is Earth observation. And I hope it will be interesting to talk. There is a lot to say about Earth observation, its capabilities, what can it do for climate change. Unfortunately, I only have 15 minutes, so I will try to compress everything. There is probably even more information in the slides from what I'm going to say, but since the slides will be shared after my talk, so I wanted to put it there so for reference, and you will see that in a moment. So yeah, my name is Edward Escalona, working for the market development team at USPA. Maybe
it's not in presentation mode yet.
Okay, it is in my screen, so maybe. So unfortunately, I will have to present it like this. I think it is a problem when I have it in the browser.
Okay.
Okay, so I think you can see it like this, right?
Yes.
Yeah.
Okay.
Yes, very good.
So you might know us as GSA, which was the previous name of the agency, which was the European GNSS agency, the Global Satellite Navigation System. And we just became USPA this year, at the beginning of the year, in which we expanded our responsibilities and basically with the objective of trying to bring most of the elements of the space program from the European Union under one single roof. And this, when I talk about the space program, I'm including the Earth observation program, which is Copernicus, the navigation systems, which are Galileo and EGNOS, and also GovSatcom, which is the future secure satellite communication program of the European Union, mostly addressed to governmental users. And the main tasks that we have in these different programs are exploitation manager for with what concerns Galileo and EGNOS, which involves basically management of operation of the infrastructure, but also the provision of the services. Also, we have tasks related to security, like security accreditation of all the space components for the 4 components that I described, but also the operational security of Galileo and the operation of the Galileo Security Monitoring Center. And then finally, we have also responsibilities, our main role is what we call linking to the users, and this involves the market development of the downstream sectors for all the different components, and this includes also supporting the business, supporting the innovation and creation of solutions, leveraging from these different systems. But concerning what is important here, that is the Earth observation, and let me briefly explain what is Earth observation. How can it be useful for you? To understand Earth observation, I have to explain very briefly what is remote sensing, which is basically involves the techniques for detecting and monitoring characteristics of an object, of an area from a distance. And when I mean from a distance, it's very easy to understand if I say, when I talk about, for example, these laser or these temperature thermometers that you are using now for checking the temperature from a distance. So basically, you are not in contact with the object that you want to measure the characteristics from, and this is basically remote sensing. And this is a simple example, but this can be done with sensors that are incorporated on the ground, but on drones, on airplanes, on boats, and also on satellites, which is basically the most common use for Earth observation. So effectively, so Earth observation is the applicability of remote sensing to monitor and detect the information from the Earth, which is the Earth and its environment. So it's also including the atmosphere, for example. So basically, we can monitor physical characteristics, chemical characteristics, and the biological systems using remote sensing techniques. And the most common use is, as I said, satellites, but you can use any other type of sensors placed anywhere, as long as they are monitoring information about the Earth. There are two main modes of gathering this information in Earth observation. Basically, there are the passive mode or passive satellites, in which we are basically measuring the radiation of, for example, the visible light or infrared, and the most common use is the reflection of the sunlight on the surface of the Earth, or different objects, or different types of surfaces on the Earth. And what we measure is the reflection that are received on the satellites, and with that you can measure many characteristics. The main characterization of the passive mode is the number of bands, or the bandwidth that it's able to capture this radiation from. And this is mostly the most number of Earth observation satellites are using passive mode. The only problem is that passive satellites cannot monitor the surface when there are clouds, for example. On the other hand, we have the active mode, in which the same satellite is emitting radiation, and the main characteristic here is the wavelength that it's being used for transmitting this radiation, and the satellite incorporates a sensor as well that is measuring the reflection of this emitted radiation by the same satellite on the satellite itself. And there are some examples like LiDAR, radar, and there are some satellites as well. Okay. Another characteristics of how to characterize Earth observation is in the what we call the resolution, which has mainly 4 elements. What we call the temporal resolution, spatial, spectral, and radiometric. The temporal resolution is basically how often do the satellites take an image of a specific place in the surface of the Earth. So how often it's revisiting this same place and taking an image, and this can range from 1 day to several days or even weeks, depending on the satellite. What now is happening is that instead of one satellite, there is a constellation of satellites that is going around the Earth. So the revisit time is much more often. So even if it's different satellite, but they are taking the same images, so you can take the images much more often. Then there is the spatial resolution, which is basically the quality of the image. So it's the basic resolution that you know the pixel size of that image or that measured element. It's and it can range from the highest resolution that is now in the market, which is 30 centimeters, to several kilometers. And of course, depending on the type of sensors and what are you measuring from the surface of the Earth. Then there is the spectral resolution, in which basically it specifies the number and the size of the bands that you are measuring. So, and this basically is the number of sensors that you are putting in the satellite. And finally, there's the radiometric resolution, that is the level of sensitivity to distinguish between 2 different measurements that are in the same range of a spectrum. And now for the downstream part, let's say, what is the applicability of all this information? This information can be used in a very wide number of applications and markets. This is just an example that of some markets and segments that are already using Earth observation, but some others that are using it very little, or there is a lot of spaces still for using these kind of technologies. And this is what at USPA we want to foster: the creation of new solutions that are using this data. of Copernicus in our case, but for Earth observation in general. And all this information and data, it's not only helping the business and to create new solutions, but it also supporting the transition towards a more green and digital environment. So it was estimated, like this is a picture only in 2017, in which the downstream market, and when we talk about downstream market, you can see here the darker blue. So the upstream is basically the infrastructure, the launch services. All the downstream value chain is composed by infrastructure providers, like cloud services, data providers, platform providers, any kind of product or service that uses Earth observation data, consulting services, and at the end of the chain, the end user. So all this downstream value chain, the value in the revenues created in 2017 was around 2.7 billion euros globally. And this is, of course, increasing and expanding. So as any other technology that we can see, it's evolving fast. Earth observation is here for many years, but we see that the advancements in the technology is really growing in the last years. We can see a huge number of satellites nowadays, which means many more data that is available for the users, much better infrastructure to support the access to the data. Also advancement in sensors. So we have now, as I said, very high resolution up to 30 centimeters, or it can be even better, but because of data privacy, it's not allowed to take images for so much high accuracy, but it's possible. And we have also better revisit time. There is a boom now of small satellites which are in the low Earth orbit. So a lot of is happening, and this together with the rise of artificial intelligence, with the cloud computing systems, this creating an ecosystem that it's very useful, and it's creating a horizon of applicability that hasn't been explored so far. With what concerns the specific case of Copernicus, so I was mentioning all that was Earth observation in general, but Copernicus is the Earth observation program specific from the European Union. And basically the main characteristics is that all the data that is provided by Copernicus is completely free and open to everyone in the world, basically. Oops. Yeah. So basically what we have with Copernicus is what we call the three components. There's the space component that are the satellites or the missions that are the sentinels, which we have several sentinels with different characteristics each. Then we have the in situ component, that is the different types of sensors that are not in the satellites, but that complement all the information received by the satellites. And then there are the Copernicus services, which are basically thematic services that you make use of Copernicus data, of the data from the satellites or in situ sensors, and provide specific services for some thematic use, like it can be atmospheric monitoring, marine services, land monitoring, climate change, security, and emergency management. And all this is generating daily more than 20 terabytes per day. So we can consider that in terms of space data, Copernicus is the #1 provider worldwide. And I'm not going to go into detail this. This is part of the information I said I would include in the slides, but these are the different sentinels that are there, their characteristics, how often they're revisiting the resolution, and so on. So you can take a look afterwards. As well as all the applications that can be that these satellites can be used for. Here I put a QR code in the slide, so you can gather much more information about all this in specific detail. So there's a lot of information. And this is basically the government, so which are the actors that are managing, let's say, the Copernicus program. So it's managed basically by the program by the European Commission, but there are the space services, which is in collaboration with ESA, EUMETSAT, and some contributing missions. Then there are the Copernicus services, as I explained, which are managed and implemented by the so-called entrusted entities. Then there are the in situ component, which are provided by all the member states, and it's coordinated by the European Environmental Agency. And then there is EUSPA as a new actor, to try to complement all the efforts in the downstream development of the downstream market, mainly focus on what we call the other users, which are mainly commercial users, not the governmental users, but more users that can create companies and products and services based on Copernicus. And in general, I wanted just to mention, I mean, you will see that in the presentations later, some specific applications, but what can EO do, Earth observation do for climate change? So it's an amazing tool, Earth observation, for monitoring a lot of things on the surface of the Earth. You can monitor deforestation, the rising of the sea levels, greenhouse gas emissions, the level of snow or ice coverage in the poles. You can monitor temperature, humidity, moisture, floods, fires, a lot of things. And all of this can support climate change and adaptation and mitigation. So you can get this data not only on the specific moment, but also historically. So you can perform a lot of analysis of what is the evolution of the situation using historical data, and you can make projections in the future as well. You can make forecasts to understand what is happening, what is the evolution, and different type of events that are happening on the Earth. But not only globally, you can also, Earth observation can have an impact also in specific sectors. For example, this is just an example on agriculture. As you might know, agriculture and forestry is responsible for more than 25% of the greenhouse gas emissions worldwide. And this is only going to become worse if we don't do anything because of the scarcity of the land, water and energy resources, and the population increase. So we need some mechanism to ensure a sustainable production of food, and Earth observation can play a huge role here. There are many applications in agriculture for natural resources monitoring, environmental monitoring, weather services, operational management, in which Earth observation can increase the efficiency and in the production of food. So this is just an example, but it can play a role in any other sector. And this here, I just put some examples of images from the Sentinels. So this is Sentinel-2. You might know the volcano in La Palma. Recently, this is an image taken on the 15th of October. So the Copernicus Emergency Management Service is monitoring the evolution of the volcano and its effect, and how the lava is evolving downstream to the sea. This is another example of floods that were monitored in April in Timor. So you can monitor many things. Here are fires monitored near Mexico City, in which you can monitor, for example, on the left with Sentinel-5, you can monitor the level of carbon monoxide, while on the right you can see visually the effect of the fire and the smoke coming up of the forest.
Edward, just to remind you that you're soon reaching the end of the time in like a minute or so.
So I will take 1 more minute. This is all the information. We want to publish this in a market report. Typically, before we had a GNSS market report, the last one was published in 2019. The next one will be published in January 2022, in which will include as well information about Earth observation. So I encourage you to download the report. You can download the previous one to see how it will look like, more or less. And in January, as soon as it will become available, so please download it. There will be a lot of useful information. And just very quickly to inform you that at USPA, we also, as I said, we foster the creation of innovative solutions. And for this, we have different funding tools. We have the Horizon Europe, Fundamental Elements, and Cassini. I will only give a couple of examples on Cassini. We have now opened a Cassini hackathon for the 5th and 7th of November with a particular challenge on connecting the Arctic. And this is usually this is for using Galileo, EGNOS, or Copernicus. And then we have another competition that it's called My EU Space Competition, which deadline 15th of November, in which we are supporting entrepreneurship and the creation of companies and products based on EU space services. And just the last slide is an event that we are holding in Prague in the 8th and 9th of November, where all this information will be explained in much more detail and with all the funding opportunities. So you're also invited to register. It's called Space Downstream Innovation Days. So you can find that information on our website and how to register and come to us and talk to us. Thank you very much.
Well, Edward, thank you so much for your amazing presentation. Thank you very much. I remind you guys that we are going to have a Q&A session later. So we recorded the question and we will go through them soon. It's time now for our second speaker. I'm introducing Andreas Kasanditis, professor at the University of Patras. He's the head of the Laboratory of Atmospheric Physics at the Physics Department at the University of Patras in Greece. His main research interests include the transfer of solar radiation through the atmosphere and the estimation of the effects of different atmospheric constituents, such aerosols and clouds. His experimental activities include measuring of solar broadband, ultraviolet and visible radiation using various types of instruments, monitoring of atmospheric parameters, as well as data analysis, quality control, and reliability of atmospheric measurement. Thank you very much, Andrea. I am leaving you the floor.
Thank you so much. Thank you, Climate-KIC, for the invitation. It's really a pleasure to be here. And may I share my presentation with all the participants. I suppose that you can see it now and it is in full screen.
Yes, we can.
Yes, great. Thank you so much. So, the topic that we're going to discuss in the next 15 minutes is about Earth observation and new challenges in solar energy resource. As you see nowadays, the energy demand is crucial. The prices are rising, and from all sides, there is a request to go as fast as possible to the new era of using renewable energies to the highest percent that we can afford in terms of the networks and the interoperability between different sources of renewables to form the energy mix. So I'm Andreas Kasanditis. I'm coming from the University of Patras, southwest Greece, very close to ancient Olympia, and we have our lab here. I'm the head of the Laboratory of Atmospheric Physics at the University of Patras. That's founded about 55 years ago. The third largest university in Greece, with a bucket of departments, laboratories, and clinics. And apart from me, that I am the guy that is doing the presentation, but not so much work. There are a group of 30 researchers, from professors to lab assistants, all full of work all days. Because we have some research activities, and you can see here the basic of them, like solar radiation resource and forecasting, weather and atmospheric air pollution monitoring and modeling, artificial intelligence in atmospheric and environmental physics. And I'm going down to very specific one, like the stable isotopes in rain and atmospheric water vapor, which is very crucial for the climate change estimation. The ultraviolet radiation, measurements, modelings, and effects on human, as well as early warning models for epidemic spread, like the West Nile virus, COVID-19, etc. So I'm going to introduce you to a term that maybe is you're not so familiar with. It's energy meteorology. So what is energy meteorology? You see here the description is the interface between renewable energy and atmospheric physics. Let me put it in a more let's say easy way. Energy meteorology is the field of meteorology that you are not interested about the typical meteorological forecast, like if it's going to be rain or not, if it's going to be windy or not. And this forecast is usually has been formed for the navigation, for the airplanes, the ships, etc. However, in energy meteorology, we are interested about how much solar radiation we have at the ground for the solar farm. So we're not interested if it's cloudy or not, but we are interested about the solar radiation. We are not interested in how it will be the wind speed or the in the before scale. We are interested about how many power we can produce with this wind. And all installation, either in solar or in wind, are highly related with the available meteorological conditions. The energy meteorologist is the guy that is walking in a field full of maps and satellite information and measurements, and there's a full group of mechanics beside him with huge trucks with with wind turbines and PV installations, and they are looking for a place to build the farm. So this is the energy meteorology, and you see here that there are plenty of applications that are related to energy and meteorology as well as the lightnings, the passing clouds that drop the solar power, the thunderstorms that can cause disruptions to energy transport, hurricanes and drought, also related to operation of oil rigs or hydropower, heat wave that change a lot the demand, as well as long-term changes like the climate change or the El Nino effect. So, and these are going from seconds down up to decades. The energy meteorology can offer to the solar sector, which is our field of discussion here, two main things. The first is that they can use the solar farmers can use high energy meteorology to improve the penetration in the energy mix and the operation in the grid in a more efficient way. Even more, when you have a large-scale application, then this demand for efficient use becomes even higher, because the introduction to the grid is very, very important. And what is maybe most important here is the international collaboration in this field and the consensus. And apart from participation in the EO4GEO project, I would like to introduce you also to this task from International Energy Agency. It's task 16 in the frame of PVPS, when where a group of experts across the world, we are discussing this issue and exchange national experience, the challenges, and all the information we can gain one to each other, and in order to resolve such issues. So, what is also important is that you may see here a nice figure that represents the part of the world in the Sahara Desert that would be needed in order to produce the to meet the energy demand for the whole globe. It's a small part of the world. However, it's not very small. I mean, it's about 1.25% of the land used for agriculture, and it's also is equivalent with the surface of the major cities. So instead of having such a huge PV plan in the Sahara, we have PV plants or concentrating solar thermal power plants across many areas, more in the south part of Europe, less but not least for the north part, and we want to meet the demand in the terms of your region, of your country, or in Europe as a whole. And how we can use Earth observation systems for solar energy. Actually, you can see here in two-axis system. Here you can have the spatial scale for 1 meter to 100 kilometers, and you see here the time scale. And you see here that the different type of instruments or models or methodologies in order to perform the best available, to get the best available information. So when you're talking about the spatial scale of 1 meter or up to some meters, let's say, imagine that you are in a PV farm and you're lucky, you are going to have a nowcast, a short-term forecast of the change of solar radiation, and this is highly correlated to PV power. We can use typical instrumentations like pyrometric sensor, and we can go to all sky images and calculate the vector of the clouds and get an idea about how the shadows will move and how much will be the production in our PV farm. When we were talking about scales from 1 kilometer to some 20 or 30 or close to 100 kilometers, and forecast times that are not so are not the same, or it can go up to an hour, even more, depending on the weather. It can go to the satellite information, and a typical service here is the Copernicus atmospheric monitoring service that can give you the information from for these time scales and this spatial scale. And then if you want to go to higher time scales and spatial scale as well, you can go to numerical weather prediction models, like the one that are provided by ECMWF. So depending on the application and the time horizon that you're interested, if you are a PV farmer, or if you want to manage the grid, or if you want to manage the grid, but for the next few days, there are different tools that they are available. And if we stick on the satellite information and we want to have a closer look about the architecture of a system that gives you such information, we have to take into account that there is a lot of sources that we can gain information. Let's say we can get the ozone from one satellite, we can get the water vapor from another, we can have the albedo, the reflectivity of the surface, which is very important. Imagine that you have a PV plant in Sahara and you have a PV plant in North Europe. The surface albedo, the surface reflectivity is not the same. We want to know the cloudiness, and these are coming from the usual images that you see in weather forecast from Meteosat second generation satellites. We're going to have the aerosols, I mean the air pollution, which, let's say. We're going to know the position of the sun, of course, and these are all together are coming as inputs in a system that can use neural networks or deterministic methods to identify the solar radiation on the ground. And then you have the product, and this can be used by a variety of users. And so this is the architecture and the strategy to provide a reliable, user-friendly information to the stakeholders by using as much as more available data that you can get from ground or from satellites. So this is a very smooth picture of the cloudiness across Europe, and if you zoom here, there is a lot of detail in this information. However, even if this picture gives you the information in about 5 to 5 kilometers, so imagine that every 5 kilometers you can have different information about the solar radiation that is available. It's never easy to get the ground truth if you're looking the clouds from space, as you've seen from satellite. because the ground truth is very much complex. And you may see here a time lapse from all sky camera here at Patras, and you see a lot of clouds passing and coming in front of the sun, which is very important, covering other parts of the sky, a lot of cloud types, thick clouds, thin clouds, etc. So the ground truth is not so easy to be estimated. However, there are a lot of methodologies to adapt the satellite data to the ground truth. So this is a huge bucket of other methodologies that are called site adaptation methodologies. So imagine that you have the satellite information for this place for a year. You have also the information of the clouds and the real measurements from the ground, and you can compare them, and then you can calculate a correction factor. If you have this factor, then and it's robust enough, of course, you can say, okay, now I can move my ground measurements, I can use the satellite information with this correction, I have a reliable estimation of the radiation at the ground. This is the usual way to do this. And what are the quantities that we want from for the solar radiation? Actually, there are three basic radiation quantities. One is the global horizontal irradiance, so it's the solar radiation that is coming from all over the sky. You have an instrument on your terrace on a horizontal plane, and you get all the radiation. And this radiation can be divided in two components. The radiation that comes directly from the sun. If you look at the sun, you get an important part of the whole radiation, and the radiation, and this is the beam normal irradiance, the BNI component, and you have the radiation that comes from all the other parts of the sky, and this is the diffuse horizontal irradiance. So you have yourself in a terrace, you get the global horizontal irradiance, you can look at the sun and get the BNI, and then you can put your hand and save yourself, and you get the radiation from all over from all the other parts of the sky, and this is the diffuse irradiance. And you can see that how these irradiance components behave in a clear sky day, from early in the morning until the afternoon. You see here that the direct beam goes very high at the beginning. Imagine yourself that you are looking at the sun, even a little bit after the sunrise, you have a lot of radiation coming to you. The diffuse radiance is the component that has the smallest contribution to the global one, which is this one. And then you want to use this in two types of solar farms. This one is a typical PV farm that uses GHI, global horizontal irradiance, and the direct component as well. Especially if the PV panels are looking directly in the south and they're not moving, then you need mostly the global horizontal irradiance. And this is the solar tower that is in the middle of some hundred of reflectors, that they get the beam irradiance, the one that's coming directly from the sun, and they move it here at the top of the solar tower. And then you have a fluid there that is getting quite hot, and you can use this thermal energy to produce electricity. This is a system that is highly related to the radiation that's coming directly from the sun, the BNI, and this is very useful for places that don't have a lot of cloudiness. Let's say South Spain is full of such towers. Morocco, also South Turkey, are typical areas close to Europe that they have such installations, and PVs are not so highly related to cloudiness, because you can have also the radiation that's coming from other parts of the sky. So,
Andreas, if I may just interrupt you to say you have 1 minute left, if you can.
Yes, thank you. So this is the counter radiation service web page. In our challenge, you will get the data because there are 2 or 3 constraints here. The first one, you have to register. So you will need some time to get the feedback from the system and have access to the data. The second one is that you can download CSV files, and you know that in your computers all Excel files are not depicted in the same way, the numbers, the decimals, etc. And the third is that there was a planned stop of the service because of some kind of internal work for backups, etc. This is not the case. It's working right now. Actually, this stop has been planned for tomorrow morning. But in order to be on the safe side, we have the data, have downloaded the data already, and it will be given to you. So you can go here, sign in, get the information, go to the next page, and you can see here. Then you select the point at the map. You can select the time period, the time step, and you can get at the end a result file. If you click here in your web, Google or Firefox or whatever, you can get the result file. And what we need from you is to meet the challenge and keep calm and use Copernicus data, and find out from 5 cities in Europe which city will provide the best revenues and the best solar potential. So a solar company is coming to you, and they want to build a new solar farm, and you have to decide which place is the best. So thank you.
Thank you, Andreas. Thank you so much for your super interesting presentation, and for having introduced the concept of the challenge that we will be moving to that soon. Apologies for my pronunciation of your name. Same apologies will go to our next speaker. I'm happy to introduce Diego Saez Gil, the founder and CEO of Pachama. Pachama is a Y Combinator-backed startup that's working to accelerate the flow of capital to carbon capturing projects, starting with forest biomass project. Pachama harnesses satellite images and machine learning to verify the carbon storage on forests, and then connects directly project developers with carbon credit buyers in an open marketplace. Prior to Pachama, Diego co-founded Blue Smart, an IoT company that raised $20 million in venture capital in Silicon Valley and China, and was acquired by industry leader TravelPro. Diego also co-founded WeHostels, a pioneering online travel marketplace, which was acquired by Student Universe. Diego was awarded with the MIT 35 Innovators Under 35 and was selected as High Impact Entrepreneur by Endeavor Global. Diego, wow. Thank you so much.
Thank you for the opportunity, and it's a pleasure to be here and share a little bit of what we do. And I'm going to share my screen to share with you guys a short presentation about our work. And yeah, I think our case is a case of a new startup applying satellite images, Earth observation in general, and artificial intelligence to have an impact on climate change. Our mission since the beginning was stated to be restoring nature, which is one of the key pillars that we have to solve in order to mitigate climate change. Of course, the first thing we need to do is to move away from fossil fuels and stop putting CO2 in the atmosphere. But after we do that, we need to, or in parallel, to be honest, we need to start restoring key ecosystems that, as we all know, trees and plants, when they grow, they sequester CO2, and that's how we can actually start to remove the additional carbon that we put in the atmosphere since the Industrial Revolution. And you guys might be familiar with the concept of carbon credits or carbon markets. So by those frameworks, corporations and governments can actually invest in projects that are doing reforestation and conservation. However, it's been historically difficult to ensure that the money that you invest in a carbon credit actually goes to have the promised impact. So our objective at Pachama was to accelerate the evolution of forest carbon markets using technologies, and specifically using satellite data and AI to do predictions about what is going on in the ground, right? And some of the key questions that you need to answer when you are funding a project that is doing reforestation and conservation is, what is the baseline of carbon on the ground? That is, how much carbon is there today on every single plot of land of the project that you are trying to support and the surrounding areas? You also need to answer the question of, what is the history of carbon in this place? Is this an area that has received a lot of deforestation in the past? Or is this an area that it looks the same than in the last 30 years? Or this is an area in which actually trees are growing naturally, right? And that will determine the business as usual scenario, upon which then you can issue carbon credits for the additional carbon that the project will help produce, right? So what we do is we effectively analyze those projects. And here, there are two examples. The first one in the left is a project that is conserving the Amazon rainforest, and that has been super effective at stopping deforestation. And you can see, deforestation on the right side of the project, and this triangle that is actually keeping the forest standing. We produce time lapses that make this, very visual to observe. And the project in the right is actually a project that hasn't succeeded at stopping deforestation. And you can see the deforestation that has happened inside of the boundaries of the project. And again, to answer the questions that I was mentioning before, we tap into what we call data fusion, which is fusing satellite data and remote sensing data from a lot of different sources into one single pipeline, on which we can train algorithms that can answer those questions, right? So one of these sources of data is radar data coming from Sentinel constellations, the European Space Agency. The good thing about radar is that it allows you to see through the clouds, right? So in places like the Amazon rainforest, this it's very common that the forests are covered by clouds a big part of the time, right? So with radar, you can actually see through the clouds and observe what's going on at any given moment. Landsat, which is a series of constellations launched by NASA, allows us to go back all the way to 1984, and we can observe deforestation over time. LiDAR is a relatively new source of data that we use to estimate the height of the trees, the structure of the forest, which are really good markers of the carbon sequestered on the ground. And today, one of the ways in which you can capture LiDAR is by flying an airplane above the forest. And there are several institutions that have been doing that. For example, the University of Arizona in the United States, the lab of Greg Asner has been collecting a lot of LiDAR data in places like the Peruvian Amazon, in places like the Hawaiian forest. So we ingest that data, we partner with these different organizations that have LiDAR, and we use the LiDAR as a sort of ground truth to calibrate the predictions that we do from satellite. Now, recently, NASA launched to the International Space Station a big LiDAR device, and in a program called GEDI, G-E-D-I, started releasing that data. And these are, again, LiDAR captures from space that through lines that cover the entire planet allows us to have also another source of calibration for our algorithms. And then finally, we also combine these data sources with field plots. This image on the bottom left represents how field plots are collected. Basically, foresters go to the ground and they select a 30-meter area, and in that area they measure every single tree. They measure the circumference of the trunk, they measure the heights of the trees, and they can come out with an estimation of how much carbon is there on the plot. And then that data, we use it as ground truth to train deep learning algorithms, and then we'll try to make predictions and be accurate at determining how much carbon is there in places where we don't have field plots, right? So today we have been able to collect 250,000 plots. Those plots generally are actually collected on the ground by universities, governments, or private companies that are actually doing projects, right? So a part of the work has been collecting all the ground truth data and use it to train the model. So there are three models I was mentioning before that we use most of the time. One is a historical model that allows us to observe historical deforestation and then eventually predict future deforestation, because deforestation in places like the Amazon rainforest follows a quite predictable pattern around roads and rivers, which are places that can be easily accessible by illegal loggers that go and cut down trees and then move those trees to the cities to sell them for products. And you can actually, as I said, have markers of risk of deforestation. The second is a validation model. And the validation model is basically being able to determine carbon stocks, how much carbon, how much biomass is there today on the forest, which tells you, what is the volume of carbon that should be protected. And then finally, a monitoring model that allows us to detect changes on the forest, right? We call it disturbance alerts. So if there is anything going on in a particular project, we should be able to be alerted, ideally in real time, so that then we can inform the project developer on the ground to go and send rangers or to be proactive in different ways to stop that deforestation. And then that information is also useful for the backers and for the financiers that want to make sure that the projects are doing well and gives us enhanced transparency. And the way that we do monitoring is basically by inputting data from Sentinel. Actually, in this case in particular, we detect changes. An algorithm scans an entire area that we request and then detects changes, and then we investigate further with high definition imagery coming from Planet, which is a company that has a daily scan of the entire planet. And then the way that we apply this, as I said before, is to analyze existing projects that then companies and financiers can back. And I want to show you a couple of examples. This is a project in Brazil that is conserving Amazon rainforest. And here the work has been, observing the area, the biomass on the area, the deforestation, historical deforestation rate, and ensuring that within the boundaries of the project, there's no deforestation expanding. And you can see here, this is actually an area in which there are, settlements that are already doing deforestation for agriculture, and we validated all the key aspects of this project. And the great thing is that this project are having a lot of impact on the people on the ground, because local communities are employed to do activities that actually protect the forest, as opposed to destroy the forest. And this is another example of a project in California where we have these giant redwoods and sequoia, and unfortunately these trees are still under pressure of harvesting for timber. And this is a project that is, conserving a key area of sequoias and redwoods. And here we did an analysis in which we match every single pixel of the images with pixels of reference areas that we consider similar or relevant to determine the risk of deforestation of each pixel. And here the redness, determines what is the volume of carbon, and then the whiteness determines the deforestation and the potential deforestation, right? And again, this is also projects that generate jobs and habitats for many species in California. So there are many other things that can be measured, right? Because these projects are not just about carbon, they are also about biodiversity, right? So in the future, and maybe a potential challenge for you guys is, how do we use this data to determine the biodiversity value of these projects? And there are different ideas that people are proposing about measuring biodiversity. And I think that those are, you know, areas that are very virgin, that needs a lot of research and a lot of work. So I'll stop there with a final message, which is that the care of the earth is our most ancient, most worthy, and after all, most pleasing responsibility. So I am grateful for all of you guys for encouraging you know, the research of application of satellite data for the protection of the planet.
Diego, thank you very much for your interesting presentation. That was very, very good. Thank you so much. I think if that we have still around our speakers, we might run a, let's say, a short 10 minutes Q&A session. So we are asking you guys, if you've got any question, just type it into the chat and our expert will pick up your question and try to give you an answer. So we won't be able to, you know, to ask 200 questions, but some 10 minutes. Thank you.
Perhaps I can start with a question which I saw in the chat, and perhaps it goes for USPA, and it's related to the type of instruments and the capacity that you would have in the future in the Copernicus program to identify the specific sources of greenhouse gas emissions. So to what extent the development of the Copernicus program entails a specific identification system to pick up those sources of greenhouse gas emissions, and to which accuracy you would be able to detect those emissions. I think perhaps this is for Edward, and perhaps the other speakers might have some also insights into this question. Thank you.
Yeah, maybe I can just give an overview of the capabilities of Copernicus, because currently there are some pollutants that can be detected by Copernicus, and there are what we call the next missions, or the next priority missions that are going to be implemented in the future, and one of them is the CO2 mission. In any case, the resolution that it's going to be provided, it will not allow you to detect a single company, what is the emission provided by a single company. You will need to complement that with in situ sensors or with more commercial information. What it will be allowed is through some mathematical models, and using this information, you will be able to infer what is the information at ground level, what is the information of let's say on a city scale, but the resolution that is going to be provided for monitoring the pollution and the greenhouse emissions, it's never going to be at least in the Copernicus program, it's never going to be at that level, with that level of resolution, to know if it's one specific company or another. At least in the, let's say, foreseeable future.
Thank you, Edward. And I don't know if Diego or Andreas has some comments based on, not necessarily on the accuracy or specifically Copernicus, but also how satellite data can help us in the process of mitigating at source the emissions of carbon dioxide and other greenhouse gases.
Well, one thing I can comment is that, as you guys know, of course, the main source of emissions is oil and gas, but another source of emissions is forest fires, right? And we need to be able to be more proactive about mitigating risk of fire. Unfortunately, because of climate change, there are enhanced conditions for fires, and that's something that I personally suffer in California, unfortunately. But you know, I think that with satellite data and AI, we can look at the history of fires. We can look at markers of fire risk, and we can probably come up with better models for predicting, future fire risk, and then using that data to inform local governments and local project developers, like the ones that we work with, to prevent fires and to try to reduce that source of carbon emissions.
If I can may also add that satellite data definitely is a great advantage. I mean, there are a huge amount of satellite data, which is becoming a problem. But here is the technology and the methodologies to deal with this. But we cannot cover the Earth with ground stations. If you want to have sufficient information about many places in the world, and this is because climate change is not only in our neighborhood. We need this information. Satellites are becoming better and better in terms of time steps, in terms of spatial analysis, and accompanied with the in-situ component, as referred previously by Copernicus, it's the best combination that we can have nowadays.
Thank you, Andreas. I will quickly address two more questions. The question is related to the accuracy. I think we are all very happy and impressed about the capacity of satellite information to give us insights about the infrastructure, the distribution of the land, and that ever increasing accuracy. The speaker was wondering, sorry, the student was wondering whether at some point you will encounter some concerns regarding privacy and and ethical elements related to the capacity that we have achieved so far, and perhaps in the future of really being able to identify really small places or locations on Earth. So to what extent this is becoming an ethical concern?
Maybe I can quickly comment. I already mentioned in the slides that now the highest commercial accuracy is 30 centimeters, but this is not really so much a technological limitation. It's also a limitation in terms of privacy. I'm not so much into the details and the legal concerns, but basically it's similarly to what happens with Google Earth or any or Google Street Maps, in which when there is a, let's say, personal information or something that is subject to privacy, this information is covered. So in terms of satellite imagery, it will be something similar. Satellite providers are satellite image providers are not allowed to reach at that level of accuracy in which the privacy of the citizens is compromised, and this will continue like this. It's already regulated in this sense. It will be very difficult to go to the level of detail in which you can see really a pixel in 1 centimeter and really have that information, unless it's something for governmental purposes, or which I'm not really concerned about.
Thank you, Edward. Any comments from Diego or Andreas?
No, for me.
So I have the final question, which is actually being specifically asked for to Pachama. And then the question is Pachama working with other types of carbon capture apart from forests, for instance, and the water fauna?
So we are starting to look at what coastal ecosystems, what analyzing coastal ecosystems would look like, and particularly mangroves forests, which are very prevalent in Mexico. And then, of course, in the future, we could expand into kelp forest and even coral reefs restoration, which also is a source of carbon removal, but it's on a very experimental phase for us. And again, I would point out to Greg Asner's lab that has been doing a lot of work on analyzing ocean ecosystems with satellite data and LiDAR data.
Thank you, Diego. And I think with this question, we conclude the Q&A session. And on behalf of Climate-KIC and EO4Geo, we would like to really thank all the speakers. And then I would give the floor to Gianmarco to continue with the rest of the program. Thank you very much.